Now it is. All right. Good morning, everyone. My name is Gautham Shenoy. I work for AMD. And today I'm going to be talking about our experiences with EVDF, both the existing one as well as the most recently presented complete one, but on server workloads. So this is like a kind of complementary to the talk that Yusuf gave yesterday. And this is like, can be thought of as a part two of the last year's OSPM presentation that we did, where we focused on a couple of workloads. So this is taking some others. And a disclaimer, so most of this work was actually done by Pratik, my colleague, and he unfortunately couldn't be here today. So I'm just presenting on our behalf and on his behalf. And Ayush is a test engineer who helped set up the machines, run these tests, collect the large amounts of data, and then help us analyze these things quite quickly. So go to the next slide. All right, a context for this talk. So last year, after the OSPM talk, what we was wondering is, what is it that the scheduler is really missing, that the workloads could ask and specify that this is what are requirements. And we've seen several talks, even yesterday, Wesson's talk, for instance. What does it mean to say, how do we present, for instance, latency hints to the scheduler? Similarly, server workloads, last time we said that we want to describe a behavior where the task would like to run for long, even if it's scheduled late in time. So what Thomas suggested is, why don't you just study a bunch of server workloads, understand their behavior? And that was what the talk was originally supposed to be. But then Peter posted EVDF complete in April, and we got nerds into evaluating that. And we saw some very interesting improvements, and we did try to understand what was the reason for those improvements. And this talk today, I'm going to be largely talking about EVDF complete, the kind of features in it that sort of make performance better, or at least bring it back to the level at which we had been in the case of CFS. And what we did was, there were a couple of benchmarks that our performance team had noticed a significant regression, primarily Death Star bench and MySQL. So we debugged that and present what was the behavioral difference there. And we also took up this Phoronix test suite and tried to see which other workloads which see significant sensitivity, and we present a couple of those. So I'll be referring to three kernel versions here. One is CFS. Then when I say EEVDF, it means the current tip core EVDF, and then we have EVDF complete, which are basically patches from Peter's Q shared EVDF. So this is the complete version that was recently posted. So we took 6.9 RC5 tip as the baseline for CFS. We reverted all the EVDF patches, and in the case of EVDF complete, we applied all the EVDF patches. So these results are from a two-socket AMD EPYC server with 128 cores per socket, SMT turned on. There are 8 last level cache domains in each socket. So that's the context. So first we'll go to this benchmark called Death Star bench. So this kind of models a social media application where a user is opening, say, something like X or Meta, and they want to read their timeline. So you have a client, there's a load balancer, there's the actual business logic, and then you have the caching and the storage layer. So a lot of these are implemented as microservices. We are just going to look at just one flow, which basically is called as the read home timeline service. So when the user first opens the app, what the timeline is going to be, which is basically a composition of all the other users that the user follows, right? So this flow is relatively simple to analyze. So it consists of a client, which drives the workload. Then you have the load balancer, which distributes it. You have Nginx, and then the actual logic is in the read home timeline application, which talks to the cache, which is Redis, and the post storage. So that's the flow. And so when EVDF was posted last year, we had noticed a significant regression in the numbers for Death Star bench. So we didn't have a lot of time at that point in time to really see why was this particular regression. But later in the year, when we did the bisect actually landed on the commit which switched from CFS to EVDF. This is basically, after we implemented all the lag-based logic, and finally where we actually do the switch from doing a min runtime based scheduling to the deadline based scheduling. That is where we saw the regression. But thankfully, we also had this particular shed feature called EVDF, which if you disable, it would go back to min runtime scheduling, right? So we thought, okay, if we just disable that, maybe we'll be able to recover the performance, but that was not the case. So it was not it was not because of either min runtime scheduling or the deadline based scheduling that was actually causing the problem. So then we did a bisect hunk by hunk, and that pointed us to this particular hunk, which does the lag clamping, right? Which would clamp the lag. And since lag is kind of important during the wake up, so we focused our debug on the wake up path primarily to see what's going on. And that's where we noticed something very interesting. So the first thing that we noticed, okay, I went too far, sorry. Noticed was this post storage server, the number of tasks came down by 40. So essentially what happens is the client sends out this request, and depending on the rate at which the requests are sent, the post storage instances, they spawn more and more tasks to handle them. So if these number of tasks themselves are going down with EVDF compared to CFS, that means that we are probably not driving enough requests. So that's the reason why we saw a throughput drop of 10%, right? And another thing that we noticed was in the case of Nginx. Now, Nginx, remember, it acts as the first responder. The client sends the request, Nginx gets the request, and then it wakes up the logic to actually, obtain the timeline information and present it to the user. So the Nginx was experiencing a very, very high number of involuntary context switches, which means that it was being kicked out way too often compared to when we had the CFS logic. So these two kind of indicated that EVDF was really very, very preemption heavy, and perhaps that's the reason why we were looking at that kind of slowdown in the performance. So essentially, what happens, and then we did some tracing to figure out what's going on. So what was happening is that when the client sends the request, it goes to Nginx. Now, in sort of a situation where the system is kind of overlaid, where so in this particular instance we were running this whole setup, the entire Death Star bench orchestration was run on a group of 32 threads, like 16 cores, 32 threads. So on a relatively busy system, when Nginx gets a request, what it does is it wakes up this read home timeline service. So as we know, during the task wake up, we try to wake up the task on the last level cache domain of either the task's previous CPU where it was run, or on the last level cache domain of the waker, which is the Nginx thread. So in the cases where it turned out that for whatever reason, based on the load computations, we decided that, hey, we need to do a affine wake up. We need to pull the task closer to the waker, right? If we do not find an idle core or an idle thread, we pilot on the same CPU where the Nginx is run. So what's the problem? The problem is that imagine that you have Nginx, which has an average runtime of something like 200 microseconds. And this home timeline service has like an average runtime of 30 microseconds. So when the home timeline service wakes up on the same run queue as the Nginx, it pulls down the average V runtime. And now Nginx is no longer eligible to run because Nginx is the average V runtime of the Nginx task is greater than that of the average V run queue average V runtime that has been computed. So as a result, there is a preemption that happens and Nginx thread gets kicked out. And since now the Nginx is no longer there, the clients which want to send the requests, they have to wait for the Nginx thread to come back again, right? And there's this extra overhead of context switches specifically because these tasks are running for such short duration. So load balance is not going to have any chance to, if there is a waiting Nginx, there's no way that the load balance is going to figure out and pull an idle when it goes idle, pull the Nginx task because it happens so fast. So that's one of the reasons why we are seeing a lot of these context switches with EVDF, which we did not happen with CFS, because with CFS you would the preemption logic was slightly different. I mean, we used mean granularity and wake up granularity, and there was this whole other set of heuristics. Not perfect, but for whatever reason, it would not kick out the Nginx task. But with EEVDF, because we have a fairly straightforward lag-based, eligibility check, which is what Yusuf also mentioned. Nginx, since it's no longer eligible to run, it was kicked out, right? So that was really the problem. So Pratik had said, and I'm kind of trying to fix it, and Peter cleaned it up, and we have this in the current tree. We have this feature called respect slice, which essentially what it does is it says if a task was eligible when it got the CPU, then let it run till its deadline, right? I mean, don't at the time of wake up, do not preempt it. Let it run till its deadline. There are advantages, obviously, because you can limit aggressive wake up preemptions whenever a task with a positive lag joins the run queue. But the disadvantage is also that if the current running task has a pretty large slice that it has set using the set slice interface, then the waking up task, if it is latency sensitive, it simply has to wait for that long. So there is this, again, a trade-off that we're looking at here. This can be elevated. There's another feature called pre-start, which basically looks at if the waking up task has a shorter slice than the currently running task, it will nevertheless preempt the currently running task. So it is possible in theory to sort of set, the waking up, the slice of the waker to a smaller value, so that it and enable this preempt short feature to preempt the current running task. But for these workloads which are like throughput oriented, and where there are this kind of important threads, and I'm using important in a kind of a vague way, where these important threads would like to run to completion, respect slice seems to be helping. And by the way, we did try out setting the nice value of Nginx to -20, giving it a smaller slice, but even that was not able to elevate the performance. I mean, from a 10% regression, the regression came down to 9%. We were not able to recover the performance entirely. So with EVDF complete, what we are seeing is that if we compare the existing EVDF and the EVDF complete, we are seeing an improvement of 10%, which basically recovers the performance. I mean, it's not like it's doing better than CFS, but at least it's going back to the stage which we had when we had CFS. And the interesting thing is, and that's expected actually. So if you see the number of involuntary switches, now that is coming down, which means that Nginx actually running to completion, it is actually yielding the CPU more often. So it's not like Nginx was behaving badly, right, to begin with. It was not like it would use up all the slice that it was given. It would have yielded it, just that in terms of if you look at this, the average rerun times of the task that was waking up and the Nginx task would invariably lose, simply because of the difference in the average rerun time that the Nginx task and this waking task had. So yeah, so the key summary is in this particular case, I mean, even though we had features such as run to parity, even though we had a combination of nice values and a shed slice, none of that helped recover the performance, but respect slice did. I know that Peter perhaps is not very happy with the feature, because I do understand that there are workloads where having this feature on by default may hurt the performance terribly for latency sensitive tasks, but it is at least good to have this feature for these kind of throughput tasks. Sorry.
Yeah, so
Peter, you had something to say?
It does hurt quite a few workloads. But yeah, we can at least keep the feature until we figure out a way to communicate some of this. One question I do have is, why does NGX wake up that task so early? If it really wants to run to completion, it could delay that wake up, right?
Peter, can you try again?
Sure. So yeah, the run to the respect slice thing, that does hurt quite a few workloads. So I'm not sure we'll keep that on by default, but I'll at least keep the feature around until we figure out a way to configure things differently. But one thing that I was wondering about is why does that NGX wake up that other task so early if it still needs work to do before that other task can actually do its work?
So
does it make sense to also look at changing user space to do that wake up later?
So Nginx is basically listening on the socket, Peter, and as soon as it receives that packet, the logic is it evaluates that and says, I need to forward it. This is like whole this microservices based thing where it says, okay, this is the microservice that I need to activate when I get this packet, and then I go back to listening on the socket, for more requests. So that is how the logic currently is integrated. So what you're suggesting is probably Nginx should queue up these requests and then wake these tasks up in a bunch or something like that. Is that what you're suggesting in the user space?
So yeah, I'm not entirely sure on how it works. Does it wake up multiple tasks, or does it wake up the one task and then that one task needs to again wait for more work to show up?
No, it's actually the Nginx. So you have several clients. Think of it like you have 10 clients, and Nginx is like acting as the first responder. So when the first client sends the request, Nginx gets it, it wakes up the worker thread, goes back to listening, it gets the request from the second client, it wakes up another home timeline service, then goes back to listening on the socket, and so on. So if Nginx is taken out of the picture, all the other workers who are, or the other clients who are there, they'll send the socket, the packet or the socket, but Nginx is really not there. So it's still in the queue. So until Nginx comes back, they cannot make forward progress.
Okay. So it ends up waking up less worker threads than it ideally would.
Yes.
Okay. Thanks.
Yes, and this is one of those pathological cases simply because it's just that these tasks run for very, very short durations. I mean, it's in microseconds. That's what we measure. Like, Nginx on an average for 200 microseconds before it goes to sleep, where this has nothing on the where the listen call basically has nothing coming in, and these home timeline services, they run for something like 17 to 20 microseconds. They are that short. So it's just the ratio between these two that is causing even setting minus nice 20 to not help, because it's simply not enough to alleviate the problem and make Nginx still eligible. Right? If Nginx were eligible, it would still continue to run, but here it just becomes ineligible just owing to the fact that this the average runtimes are so far apart.
Right. I mean, it really doesn't make sense to have these client workloads be split over so many different threads, but I mean, that's what it is, so we need to deal with it.
Yeah.
Okay.
Right. So yeah, thanks. So this was the first behavior. The second behavior was, again, this was reported by a performance team. They move kernels once in a while inside AMD. So they used to be on 6.6. For some reason, they decided early April or so that they want to move to 6.0. They moved to 6.6. And 6.6, they saw a massive regression on one of their MySQL, the sysbench workloads. So the way it was set up is you have sysbench clients which are pinned to a group of 32 CPUs, which is spanning in 2 LLC domains. And then you have the MySQL setup, which is pinned to another socket, again, 2 CCXs. And the sysbench basically acts as the client which drives the query. And the test that they were running was the OLTP queries. This is a read-only test, big table, 3 big tables of 10 million rows each. And when we did some tracing, the way we figured out was there is one MySQL D thread which acts as the first responder. And when it gets a request, it wakes up one of the threads, other MySQL threads from the pool to handle the entire query. And that thread essentially is relatively longer running. It does the entire query processing, right, from optimization to query cache lookup, and if required, get more data from the backend, right? So this is the setup, and they reported a 10% regression when they moved from 6.0 to 6.6. We knew that EVDF had gone into 6.6. So again, doing a bisect, we landed at this lag-based placement, which was showing the problem. So I mean, just to give a recap, previously before this patch was there, the way the vRuntime was computed whenever a task moved run queues was that we take the maximum of the tasks or the shed entities vRuntime and the average vRuntime of the run queue where it is going to, when we subtract something from the shed latency. So that's how it used to work in CFS. But with the lag-based mechanism, we know at the point when the task was moving, what was the lag, what was the time that the scheduler owed that particular task, right? So we normalize that lag against the task priority, and then we just subtract that from the average vRuntime. So if the task was owed, it had a positive lag, that means that it is going to remain eligible. On the other hand, if it had a negative lag, it would no longer be eligible even after it moved, right? So that is the difference between how it was previously versus what we have right now. So I mean, we have a couple of hypotheses why this regression is happening. One possibility is that when we have tasks with large negative lag which get migrated, right, that lag remains. Like for instance, if they ran for some time and there was a large negative lag and then they went to sleep, subsequently during the wake up, they were woken up on some other CPU which was busy. But because of the way we are doing it, we maintain that negative lag, and they are now no longer eligible to run until the current running tasks, either completes or it runs long enough for the average vRuntime to move forward. And on the other hand, you have tasks with positive lag. When they wake up, they'll aggressively bring down the average vRuntime, and thereby making the currently running tasks ineligible. So we have two features in EVDF complete that kind of address this problem. We already discussed respect slice, which tries to address the second point here when tasks with positive lag wake up. If we do not want them to prevent currently running tasks, but what about tasks which have accumulated a negative lag, gone to sleep, come back, woken up, and they're still not eligible? So how do we fix that? So again, when we look at some of the statistics, the story is the same with EVDF. When we compared it against CFS, the involuntary switches for MySQL D was very, very high. I mean, it was over the roof. We were switching it way too often. We know that EVDF looks at the deadline, and I mean, even if there are just two tasks on the run queue, previously we would allocate, I think, shed latency by 2 to each of them so that they would run for a longer duration. Then you would do the switch. But now, as soon as the deadline is over, we do a context switch. So we have this particular behavioral difference between CFS and EVDF. The other thing that we are observing is that the migrations are high. So we don't know why that is the case yet, and we don't know whether that has anything to do with the regression. We know that it doesn't positively correlate. I mean, even in the good case, the migrations still remain high, and it doesn't seem to have any impact on the performance. But the involuntary context switches, which is active preemption, yes, that is a problem. So we have another feature in EVDF complete. It's called the delayed DQ. Essentially, what used to happen, or what happens right now, is that whenever a task goes to sleep, you compute the lag, right? And then you remember that, and you don't decay the lag or something like that. So whenever the task wakes up, it wakes up with that exact lag. So with the delayed DQ, what we do is, when the task wants to sleep, you do not remove it out of the run queue, you retain it on the run queue, and you do not compute the lag at this point. You allow the rest of the tasks to run, and when the scheduler picks this particular task, which has gone to sleep again, it is at that point where you compute the lag and then take it out of the run queue. So now you have given it some chance, you have given some chance for the average runtime to move forward, right? So so that you do not penalize this particular task. For instance, if it had a negative lag, when the existing tasks run for a while and this is still not eligible, the average AV runtime of the run queue would have moved forward. So at this point, when you compute the lag, the negative lag may have turned into a positive lag. So which means that when the task now wakes up, it has a potential to run rather than block. So this is the delayed dequeue feature. And we did see with EVDF complete that we were recovering all the lost performance mostly. And but we didn't know which was attributing to this, whether it was the respect slice or whether it was the delayed dequeue. And here, what I'm presenting is the split. So you see that when we went from CFS to EVDF, we had a 9% performance drop. With EVDF complete, that performance dip just came down to 1%. But a lot of it was actually, I mean, even the without respect slice, when you had the delayed dequeue feature on, you still see that it has brought down the performance drop from 9% to 3%. So delayed dequeue is playing a part. But if you don't have delayed dequeue and you just have respect slice, that also is bringing up. So we still don't. I mean, respect slice is definitely helping because it's a big hammer. It just says that the tasks keep running as they were, if they were given the CPU. Sorry, Peter. Yeah.
Yeah. So a few slides ago, you also said that the slices were a lot shorter with EVDF, which is true. I mean, but with EVDF complete, you can also very easily tell your workload to use a longer slice.
Right.
So that's another tunable that you might try. Just give it a bigger slice.
Yeah, those are the experiments that we've not gotten to on this particular workload. We tried that with Death Star Bench, but not with this one. So that's something that we want to explore. But with Death Star Bench, we did try a combination of nice values and the shed slice. That didn't help. So here, perhaps we will be able to tweak a bit. So essentially, where I'm getting to is the respect slice feature is a big hammer, and it's giving us a positive impact for a lot of these throughput-oriented workloads. But it would be nice to get the combination of, say, the slice value and the nice values to achieve the same impact, so that we don't have this big hammer and we can do it at a per task granularity. Because right now this is at a system-wide granularity, right? So ideally, it would be good to have kind of respect slice at a per task for each task, not for every task. So there may be tasks which we want to mark as, hey, this is my first responder task, which I do not want to switch out too often. But I'm okay with the other tasks being context switched out. Today, respect slice it's a global thing. So ideally, the best thing is use a combination of nice values and the shed slice to achieve the same effect. But we need to do some work to get there.
Yeah, so it's trivial to add a interface to set the respect slice per task. The problem is then we're stuck to that interface forever.
Yeah.
So yeah, it needs a bit of thinking if we can do it without adding an interface, and if we need to add an interface, is it an interface that can be forever more supported? And difficult.
Another thought that I had was, I mean, is it possible that we actually take into consideration the context switch overhead, Peter? Because we know that some of these cases, the tasks really run for such short durations that the time taken to do the context switch might be relatively higher. So if we know that the slices or average runtime when they yield the CPU, right, it is short enough, we do this respect slice only for those. It's a heuristic, I know, but still taking into account the cost associated, because it's really the context switch overhead that is hurting us here.
Yeah, we can try. That shouldn't be too hard to do. So give it a go, see what it does.
Yeah, okay. I have 15 minutes. Okay. I'll run through the other two quickly because I want to get some feedback on others. So the next two things are from the Phoronix test suite. So we ran a whole bunch of them, and these two showed significant improvement. One was this memcached benchmark in Phoronix, which uses the memtire benchmark as the client. And then you had the memcached server. Again, the same model. You have a first responder thread that gets the request and then wakes up one of these MC workers from the worker pool that actually does the lookup on the hash tables, LRU, and other data. So Here it was configured in such a way that we had 512 threads totally. So memcached would create a pool of 512 worker threads, and there were 512 memtire benchmark threads, and they were like running separately. So each time a request would come, memcached would pick a worker thread in a round robin fashion. So it's really, I mean, there's no way to control which request goes to which helper, right? So it can be very, very arbitrary. So yeah, and they use lib events to communicate between the various threads. The interesting thing about memcached is existing EVDF actually helped, unlike a lot of the other workloads that we saw. So EVDF over CFS was actually better, but with EVDF complete, we see a 23% improvement. This is consistent. This is like very low run-to-run variance. It's very, very consistent, which is why we have picked this particular task to highlight. And we see that, again, across the board, we see a drop in the overall context switches. The migrations are still slightly higher, but the involuntary context switches come down significantly, and the overall context switches do come down significantly for the memtire benchmark. And if we did a split and went back to the current EVDF to see how much performance improvement we got, it was still 7% better, but EVDF complete makes it, again, all the more better. Once again, respect slice had a role to play. So we've not done those fiddling of the knobs yet, but just out of the box, we see that this improvement stands. So one other, I mean, in all these three workloads that I've discussed, one pattern has been consistent, that we are seeing an increased number of migrations. It is not hurting us, but what we don't know is if we can somehow contain that, will that actually help us even more? So if the migrations are happening for better work conservation, that's a good thing. But if it's happening unnecessarily, then we may have to debug this and figure out if we can do any better. So that's something that we would like to look at next. So yeah, I mean, migration, we still don't know that. And the last one that I'm going to be talking about today is this thing called Graph 500, which basically creates a very, very large graph with a scale factor of 26, which means that there are going to be 2 power 26 vertices and an edge factor of 16. So each vertex will have about 16 edges going out of it. And there are two things that this particular benchmark tries to evaluate. One is it does a BFS. So it tries to search for some 64 random keys generated from the vertex space and tries to find those in this large graph, and then computes how many edge traversals per second did it do. And the other second thing that second test that it does is it tries to do this single source shortest path computation. So you take a vertex and you compute the shortest path to every other vertex in this large graph. And then again, you compute how many edges you've been traversing. So there is, I mean, from the reading the code, and I'm not an expert in Graph 500, but from reading the code and looking at the scheduled patterns, it looks like they have partitioned the graph into several partitions, and there's one main thread that is working on each partition. And with BFS, what you do is you have the current frontier, and then we want to compute the next neighbors, right, which have not been visited. So there is some scope for parallelization, and they use either OpenMP or MPI to do that, to do the next frontier computation. So there is 2 levels of fragmentation. One is you have fragmented the large database into multiple components where you have each thread working on it. And further, within each component, it looks like they're spawning these OpenMP threads to do the computation. So we saw on this 512 thread system, we saw 256 relatively longer running threads, and then another 512 shorter running threads, which seem to be these threads that were spawned by the OpenMP. Here we are again not a whole lot, but we are seeing a consistent improvement of 5% on the breadth first search, consistent improvement of 4% with the single source shortest path. And this is an interesting benchmark because the number of migrations actually go down here. Unlike all the other workloads that we have seen, the number of migrations go down, while the number of context switches go down with EVDF complete. So again, we've not debugged this further, but this is another thing that I wanted to share. And I mean, in summary, like I said, for a lot of these throughput-oriented server workloads, there seems to be a pattern where we have certain important tasks which would like to run to completion as long as they're not badly behaved. Respect slice kind of gives us this feature, but as Peter said, if it's a big hammer, then we still have to find out what is a better alternative to achieve the same effect. Another thing is there are a lot of workloads where we are seeing a run-to-run variance, significant run-to-run variance, but this is not due to EVDF alone. I mean, we are seeing the similar thing on CFS. So I've not mentioned any of those workloads. We still need to figure out if scheduler component there or something else that is causing the run-to-run variance. So there are more micro benchmark analysis that Prateek has posted earlier this week on LKML. Unfortunately, we are seeing regressions there because Hackbench, Tbench, these have a pattern where they do these wake-ups way too often. And there, interestingly, the migrations, the number of migrations that we are doing are actually lower. So we are not migrating the task as often. So one hypothesis we have is that because of the delayed DQ feature, because the task remains on the run queue, at the time of the wake up, right? Because since it's still there, is it likely that it will be woken up there, even though it is busy, rather than us exploring? I mean, is that code properly audited? Is one of the things that we were looking at. But more debug is needed there. So, and this is the time for discussion. So, a question here. I mean, since slice seems to be so important, getting the slice value right seems to be so important, and it's quite possible that today the value that we have, the out of the box value that we have, has been computed using some heuristic. So we take some value like 750 microseconds, and then we scale it by the logarithm of the number of CPUs, and then we determine that to be the default slice on that particular platform, right? The question is, since the scheduler knows that from the time the task woke up to the time the task slept again, this is the total amount of time the task actually did some useful work.
That's not actually true. And we had this subject yesterday. The scheduler does not know the actual work length because the wake-ups and sleeps, they can be very random due to things like log contention and IO and anything else. So the user task waking up because a new job starts and or because it just got a log or because IO completed are indistinguishable from one another, which is where I think Daniel suggested adding a hint, not using scheduled, to indicate to the scheduler where jobs indeed do start or finish. And so yeah, currently it would be best if user space does this itself. And then we also touched upon the DVFS angle of this, that measuring a slice in runtime will differ depending on how fast your CPU is running. But yeah, so if the scheduler does not have sufficient information to do this.
Peter, just curious, the kernel sort of has that information. So when a user space does go to sleep, the kernel actually knows why. If it's on IO or if it's on just sleepy, if it's on it calls a sleep function. Would it be possible for the kernel to pass information to the scheduler?
For some of them, yes. I'm not sure if it is sufficient. For example, if job completion or job start is managed with a few tags, but also user space logs are managed with a few tags, then all we know is we woke up from a few tags, but we do not know if a job is complete or if we had log contention.
Right, but that's just one case. But a lot of things, like I'm sure, like the Nginx is probably blocked on a socket.
Yes.
So if you're blocked on basically, if you're constantly, sleepy or waking up from a socket, things going back to sleep on a socket, that seems to be.
Yep. But we never know if that socket is in the middle of the operation that they do or not.
Yeah, because it could go to sleep on a socket because it received half a frame. I mean, suppose your XML remote procedure call is 16 kilobytes of data, and you received 4K or however big network packets are today. So you receive some data, but it's not a complete set. Is that then a complete activation, or is that half an activation?
But I'm saying you can still take a heuristic from that. If it's,
Yeah, but we want to move away from heuristics, because the fun with heuristics is we always get it wrong.
Yeah, or better, we could try to figure out this automatically before guessing, but it doesn't scale up because we would always have to change what we're guessing or not. Is going to sleep on a socket the end of the execution or middle execution? Then one person would complain in one way, other person would complain on the other way. It's hard to characterize, to generalize this. It doesn't scale.
Right. Well, the thing is, if we want to have user space do something, that means we have to modify every single user space application, which will never happen.
You guys
know, but it will happen for the cases where people actually care about.
I guess if you can show a big improvement by probably modify a benchmark, maybe people can be.
What do you think?
We have tried out. I mean, I'm game to trying these things out. So because right now we are running blind in several cases, and if you just let the user space pick a value, we've seen that they put arbitrary values, which is not going to help either. So
now, if you had a pluggable scheduler that you could define what to do.
But only for your one workload, and then you run another workload and you're up a creek without no pedals on.
Well, isn't that kind of a rationale for a pluggable scheduler if you have different workloads?
Everybody has different workloads. Have you seen how many different tasks were set up in that Death Star thing?
Yeah. But for the system, usually, like every system has its own type of things that they want to balance for. But anyway.
But all it matters is Chrome. Come on. You guys have the code.
I'm not sure how setting the slices here maps to the previous part, because eligibility and lag are going to hurt you regardless if you have the right slice or not. So the delay DQ helps remove the impact of lag, and then respect slice helps remove the impact of eligibility in certain cases. And you'll still run into that regardless of what slice value you pick. So I guess my question is, does this slide relate to the other two features you mostly talked about?
So regarding the respect slice part, I mean, if we know for a fact that the slice value is not as large and it's more or less equal to what the workload really wants, the timeline is more realistic right now, right? So right now, I mean, today, because the slice value is arbitrary, the deadline is computed using that thing, which means that this task could be somewhere in the timeline, which is not really the case. For instance, Death Star Bench the Nginx would have finished much earlier, but because you provided a very large slice value, the next time that it gets picked also, right, when you're evaluating which is the task that you want to pick next, it may be further off. So that's the part that I was trying to see with the slice. But yeah, you are right. I mean, in terms of eligibility, it's the nice values which today control, because it's how fast your V runtime progresses, or how fast or slow your V runtime progresses, and the average V runtime that you're looking at. I completely agree. And that's the other part, right? I mean, this is going back to Wesson's talk yesterday. So with the two interfaces that we have today, can we cover all sorts of cases, or do we still have cases which are not covered by this combination of nice and slice, right? Nice and slice really are the two interfaces that we have today. We've shown that in case of Death Star Bench, for Nginx, that's really not helping. But how can we improve this to achieve the same effect? So that was another dimension. And if there are use cases where this is not sufficient, what should be that other interface? But that, I guess, requires a longer discussion. And the last part was, okay, if we say that we do not want to set these slices in in the scheduler automatically. What are the kind of tools that we can help at least people analyze the behavior of their applications so they can set more realistic values? I mean, how can we make it easier for, say, system administrators or people who are running these workloads, tune these things better? So what kind of tools? Yeah.
Well, you would need to start actual tracing stuff and look at the activations. I think it really is easier to actually change the applications to runtime compute the slice length and update it as is. Many of the examples that you've shown today are typical work queue, like we get a work, we do a work, we're done. I mean,
Yeah.
A lot of applications work that way. And it's a simple matter of doing a timestamp before you start work and after you're done work and communicating that. It's not rocket science.
So we basically need something that helps do the slice marking inside the application. So some sort of a hint.
Right.
Okay. We'll try that out.
I mean, we can endlessly start guessing and divination, but I mean, the crystal ball instruction still hasn't been implemented.
And also, sorry, then I think it also relates to the discussion we had before about pipelines. I mean, it's a different type of kind of application, but still it's information that is there from an application point of view, but we have to guess the information. So maybe I guess we're missing the right interfaces to describe this.
Yeah, so I missed that whole pipeline. This is the software pipeline problem, right?
Yes, that's
so I came in the middle of that. I was a bit late this morning. So I was thinking that UMCG might actually be able to help with that, especially when combined with proxy execution. UMCG would allow user space to express this dependence on tasks more readily than what we have. It's just one of the many other things that I never got around to change.
Right. Since I'm run out of time, I just want to edge some of our colleagues here, KVS, Akash, and Advait, who did a lot of the initial debug before they dumped the problem on us. And this is courtesy AMD Legal, and thank you very much.
Okay, so we taking a break now, back in 15, so 10:45, sorry.
And as said yesterday, it's not just hair. You just